The objective of this video is to establish a procedure for extracting transfer functions from Bode plots, and then to work through several examples. So for the most part, this is not new theory, but we're going to work with theory that we've established in previous videos to build up a methodology that we can go from a transfer function like I've drawn, so that we can go from a Bode plot like I've drawn on the left here to a mathematical transfer function in the Laplace domain. So express that transfer function in terms of poles and zeros. And I want to start by reviewing what the gain plot of a pole and an inverted pole looks like. So on the right side, I've shown the gain plot of a pole, and below that an inverted pole. And let's update this to reflect the starting and ending decibel gain as well as the slope. So a regular pole starts at 0 decibels, and then at the pole frequency, it begins to slope down by -20 decibels per decade. An inverted pole starts by sloping upwards at 20 decibels per decade, and then at the pole frequency, it becomes equal to 0 decibels. So the key details here are that with a pole, you know it always starts at 0 decibels, and then as frequency goes to infinity, it goes to 0 gain. Whereas an inverted pole always starts at a 0 gain, or -infinity decibels, and increases at a rate of 20 decibels per decade until you get to 0 decibels. So these behaviors are opposite. The pole starts at 0 decibels and ends at -infinity decibels, whereas the inverted pole starts at -infinity decibels and ends at 0 decibels. So they have this complementary shape, you can say. Now, moving to the plot that we want to extract the transfer from, so on the left side here, we worked through an active learning exercise in class, and a question came up frequently about how we can extract the transfer function from a Bode plot if I haven't told you whether the poles and zeros are on the left half plane or the right half plane. And that's a valid concern. With this gain plot as it is, you don't know enough information to say whether the poles and zeros of it are on the left or the right half plane. You'd have to look at the phase plot. But I made the remark at the beginning of this unit that for this class, unless you're explicitly told, it's fair to assume that a pole or a zero is in the left half plane. We do sometimes consider right half plane poles and zeros, but we will be explicit about when that's the case. So if I give you a transfer function or a Bode plot like this, then you can assume that all the poles and zeros are in the left half plane. So you can come up with many equivalent ways to extract the transfer function from this Bode plot. We're going to quickly discuss two methods that you may pursue, and then come up with a set of rules or guidelines that can help you do this systematically and methodically with future Bode plots. So for method 1, we're going to look at this transfer function as being composed of a pole and an inverted pole, as well as a DC gain. The DC gain portion is fairly easy to see. You can see that we can imagine this as having a constant transfer function of magnitude g0 spanning across this plot. And then if we look on the left side, we could imagine this being an inverted pole that looks like this. So it has the same frequency as omega 1, but it ends at a gain of 0 decibels. So that if you combine the constant gain transfer function, the red line, with the highlighted brown line, you'd end up with this right here. So if you multiply the dashed red line with the first brown line I drew, you'd end up with this brown line that I just drew. So we can see this is a combination of those two transfer functions plus a pole that occurs at frequency omega 2, and the pole would start at 0 decibels because that's what poles do, and at omega 2 it would start branching down. So if you multiply these three transfer functions in the Laplace domain, you add them in your Bode plot, and you'd end up with the brown line that we've drawn. So you can write this out down below. A combination of a pole and an inverted pole. So our inverted pole, remember that transfer function is 1 over 1 plus omega IP by S. And that corresponds to this term. And our pole has a transfer function in the form 1 over 1 plus S by omega P, which is, of course, this term over here. So the second approach that you could have taken is to do this purely in terms of poles and a zero at the origin. If we have a transfer function for a pole, or a zero at the origin that goes off like this, we would want to add to it a transfer function for a pole at that frequency, which was going to look like this. And so if you add these two combinations, you're going to get a flat line that goes across the top at magnitude gain 1. And then if you add yet another pole at frequency omega 2, you'll get your Brown transfer function. So now we had three operations. We had to combine our zero at the origin, which was this, with one pole and a second pole. And we have one more thing we have to do, which is we have to figure out the gain for that zero at the origin. So the transfer function for this is, when we want this transfer function at a frequency of omega equals omega 1 to be equal to G0, which tells us that K is equal to G0 divided by omega 1, which means that this thing is G0 over omega 1 times S. And if you're getting confused at this point, that's slightly the point. I'm trying to show you that the second method is more complicated. But it works, it's equivalent. So we'll now combine our two transfer functions, our three transfer functions. So we're going to combine this transfer function here with this transfer function here and this transfer function here. So we end up having G0 over omega 1 times S. Okay, so we have a new transfer function, and we notice that they look different. Method 1 and method 2 gave us two different equations, but if we look close enough, we can see that we have some equivalent terms. So for example, this right here is totally equivalent, and we can decide to work with this term right here to see if we can get into the form of our second transfer function. So let's call this G1 of S and G2 of S, and we know that they must have to be the same thing if we did our job properly. So remember how in our previous lecture I had noted that you can rewrite an inverted pole in terms of a zero and a regular pole. So let's go ahead and do that. And notice that when we have done this, we now have this term right here, which is equal to this term. And if we multiply G0 times this term right here, we end up getting the same expression as over here. So in other words, we have proven that that G1 of S is equivalent to G2 of S. Okay, great. So we had two approaches to do this. One approach required a lot less steps, and that was this method 1, where we made use of this inverted pole. The second approach was completely made up of our primitives, of our poles and zeros, and didn't have to do any of this business of inverted poles and inverted zeros, but it was more complicated to calculate. And the reason it was more complicated to calculate was because of the way that the information was given to us, because we were given a gain that occurred here in the middle of our frequency range, and we had to navigate both to higher frequencies, which is relatively easy with poles and zeros, because a pole and a zero always starts at 0 decibels and then goes to something else. So that was simple enough. But we also had to navigate towards lower frequencies, and that's where things got complicated. Regular poles and zeros don't end at 0 decibels, they begin at 0 decibels, and so we had to do this calculation up here in order to normalize our transfer function, in order to figure out what the DC gain or the constant gain should be of our transfer function. And that's where things got a little bit complicated. Not impossible, but a bit complicated. So let's write out a methodology that can be used to to simply calculate the equivalent transfer function from a Bode plot in a systematic fashion. So in a typical scenario, you're going to be given the gain of a transfer function and the frequencies of some poles and zeros, because this is a Bode plot. So in a Bode plot, you can always look at the plot and figure out the gain in some location, and then easily see the inflection points, the poles and zeros, the frequencies that they occur at. And I want to comment here, just briefly, that when we are given this information, the frequency and the gain at one location, we don't also get to specify the frequencies that we have our gain crossovers at, because that is totally determined already for us. Because we know the slope at these locations, and we know the corner frequencies up here, as well as the gain, we don't also get a degree of freedom in selecting the gain crossover frequencies. That's just a function. That's just a property of the transfer function. It's already constrained and determined. You can calculate it, but you can't specify it. So our rules are that we're going to start at a known gain. And what do I mean by that? That means that if we know our gain at some location, for example G0, we're going to start at the frequency that corresponds to that known gain. So we're going to start right here where I've drawn this black line. And that's going to be the first term in our equivalent transfer function. We're going to multiply our equivalent transfer function by that known gain. Second, we're going to move to lower frequencies and note changes in slope. And what do I mean by changes in slope? Well, as we go from the location of our known gain and work towards lower frequencies, we see that suddenly at omega 1, our slope starts to go downwards at 20 decibels per decade. So we're going to note the frequency that happens and the fact that it went downward. And if our slope decreases by 20 decibels, as we continue to go to lower frequencies, we have an inverted pole. If our slope starts to increase, or it increases by the rate of the slope, the change of the slope increases by 20 decibels per decade in the positive direction, then we have an inverted zero. And you can check all of this against the Bode plots that we constructed in the last lecture for our poles and zeros and inverted poles and zeros. So we're going to start here, and we're going to walk towards lower frequencies and note any changes in our slope. And that's going to correspond to inverted poles and zeros that we multiply as terms of our transfer function. Next, we're going to go back to our known gain location, and we're going to move to higher frequencies. And we're going to again note changes in the slope. If our slope starts to decrease by 20 decibels per decade as we go to higher frequencies, we have a pole. Not an inverted pole, but a regular pole. If our slope starts to increase by 20 decibels per decade, we have a zero. And again, these are identifying the building blocks. These are identifying these transfer functions that we're going to be multiplying together to form our complete transfer function. So let's give this a try. This is fairly abstract at this point, and I think it's going to help to firm this up in a few examples. In our first example, we have this transfer function here, and we'll practice now extracting the transfer function from the Bode plot. Again, assuming everything is in the left half plane. So we'll notice that our gain is specified in this region right here. And we have a gain of G0. So if we start writing our transfer function out, we'll start in the center, and we say that we've got our gain of G0. And then we're going to walk to the left. We're going to go to lower frequencies. And as we go to the left, we see that suddenly we start decreasing at negative 20 decibels per decade. Remember, this is negative 20 decibels per decade as we move to the left. So if we were moving to the right, it'd be plus 20 decibels per decade. But according to our rule, with negative 20 decibels per decade, we have an inverted pole. So we'll add that to our transfer function. We'll multiply it in. Now we keep going further to our left, and suddenly our slope starts decreasing by an additional negative 20 decibels per decade, so that now it's at negative 40 decibels per decade. which means that we have yet another pole. And I was saying the words pole, but I actually meant to be saying inverted pole. So we have inverted pole because we're going to the lower frequencies. If we're going to higher frequencies, we were talking about poles and zeros, but when we're going towards lower frequencies, we're talking about inverted poles and zeros. Okay, great. So now we've walked all the way to the left, and we can start moving to the right. So moving to the right from where our gain is known, we come across a negative 20 decibel per decade point. So this is now a normal pole. And you can check that against the rules we created. So right now we're moving to higher frequencies, and we came across a negative 20 decibel per decade slope change as we move towards higher frequencies, which corresponds to a pole. Continuing further on this path, we suddenly see a slope change of plus 20 decibels per decade because our gain stops decreasing, and that corresponds to a 0. So we now have our transfer function. If we want, we can clean this up a little bit. Okay, so this demonstrated following the procedure that we just came up with. Let's now do another example, and this time I'm going to have you do some of the work and then compare it against what I come up with. So I'd like you to extract the transfer function g of s from the Bode plot that I have sketched up here. Press pause and press play when you're ready to resume. So you should have come up with a transfer function that I've expressed here by following our procedure. When we start at the known gain point and we walk leftwards, we encounter an inverted pole at omega 1. And now we're ready to walk towards the right. So as we walk towards the right, we encounter a pole at omega 2, which is down here. We encounter a 0 at omega 3, and then a 0 at omega 4, and finally a pole at omega 5. I now want you to consider the case where instead of giving you G0, I've given you G1. Now use our procedure to extract the transfer function from this Bode plot and write it beneath your current expression. So down here, you should have something times G1. And you should end up with 3 quantities, like we've shown above. So press pause, and then press play when you're ready to resume. Okay, walking to the left from G1, we encounter an inverted 0 at omega 3, an inverted pole at omega 2, and an inverted pole at omega 1. And so walking to the right, we can see that we encounter an inverted 0 at omega 4, which I've already labeled down here, and an inverted pole at omega 5, and I can see that I have a small mistake, and your inverted pole at omega 5. Okay, so we're again left with this paradox that we should have gotten equivalent transfer functions, because you don't get to specify both G1 and G2. The relationship is already baked into your transfer function by specifying a gain. You only get to specify a gain in one place if you've specified all your poles and zeros elsewhere in your system. So let's work with our expressions down below. We can see that this term and this term are equivalent, and this term and this term are equivalent, and so the difference is in this region here. And we can see that we can express our inverted pole and inverted 0 in terms of normal poles and zeros. Which now creates a match of these terms and shows us that G1 of omega 3 times omega 2 must be equal to G0. And this is true. It's actually an interesting observation because you can see from this expression the ratio of omega 3 to omega 2 is this geometric distance that you have up here. So in summary, we have We have worked on establishing a procedure for extracting transfer functions from Bode plots, and then worked through some exercises on using this procedure. Our procedure is a set of steps that we've outlined right here. It's a useful engineering tool for design analysis of regulators and closed-loop regulator design.